Okay, guys, this is our reactants, products, and sandwiches simulation. This comes from colorado.edu. I call it the PSci site. These guys are smart. They give us a lot of cool apps, and they do a great job of explaining. We used it for some of our physics earlier in the year. We've used it a little bit, I think, already in our chemistry study, and we'll look at a PhET simulation for our study of electricity in the future here. Okay, so it says I can identify the reactants and products in a chemical equation and explain how reactants form products. Okay, so up front it says how many cheese sandwiches could I make if I had 5 pieces of bread and 3 pieces of cheese? So this is before starting the app. This is just your answer on this, right? And so this is a guess, right? We're going to make a prediction. There's a little bit of scientific method here. We're going to make a prediction. I would say that with 3 pieces of cheese, I could probably make 3 sandwiches, but I would need 6 pieces of bread to do that. So let's say sandwiches. Why can't I make more sandwiches with 5 pieces of bread? Each sandwich requires 2 pieces of bread. You can't make a water molecule with just 1 hydrogen. You can't make a sandwich with just 1 piece of bread. Imagine a molecule of CO2 as a sandwich. How do you think the bread relates to making CO2? The bread, I think, would stand in for hydrogen, right? We could compare the bread to hydrogen. Or I guess in the case of CO2, I'm sorry, we could compare the bread to oxygen. Sorry, I was still thinking of water. So we look back at our notes. This is an important question. Why do atoms come together to form compounds? Why do atoms hook together to form compounds? They do this to become chemically stable. In other words, to satisfy remember the opposite rule. It says that atoms like to have 8 electrons in their outer shell. I mean, not that atoms really like anything at all. Atoms are just atoms, but I think you take my point. Okay. Atoms come together so that their outer shells are full of electrons. Okay, the instructions tell us search Google for PhET reactants, and if I do that, it'll bring me here. And it says click sandwiches. All right. Number 5, it says test problem 1 from before. So let's look at problem 1. How many cheese sandwiches can I make if I have 5 pieces of bread and 3 pieces of cheese? So 5 bread and 3 cheese. Well, look at that. I have 2 sandwiches. Was that right? Yeah. Yep. 2 sandwiches. Now, some of you might be getting frustrated at this point that we were talking about chemistry and now all of a sudden Mr. Van Wyn wants to talk about sandwiches. But hopefully you guys can see why we're going to the trouble, right? This just sort of makes it simple for us to consider at this level. Okay. Next, we're going to click molecules. So we're going to go back, click molecules. The question is, how many H2 molecules and O2 molecules do I need to get the atoms to react? So I have a bunch of hydrogen gas. I'll put it into the container. I'll put some oxygen gas. Oh, look, I need, I need 2 molecules of H2 and 1 molecule of O2. Okay, 2 H2 plus 1 O2 for it to react. If I have less hydrogen, it won't react. it won't give me any H2O. Okay, so that's my answer. How many molecules do I need? You have to forgive me for not having subscripts in here. It'll take you a second to add those. It always does. Google Docs doesn't like to oh, what is that? Yeah. I need 2 H2 molecules and 1 O2 molecule. Right, what are the reactants? Well, it's this. So my reactants. My reactants are the H2 and the O2. What are my products? The products are right here. They're on this side. They happen after the reaction on this side of the arrow of time. Okay, on this side of the arrow, we'll just call it the arrow, the yield sign. What are the products? 2 H2, 2 H2O. Right here is 2 H2O. 1, 2, 2. How much more H2 molecules do I need than O2 molecules? So I need 2 H2. So it's a 2-to-1 ratio. Okay? I know that ratios might have freaked you guys out across the hall in your algebra class, but here we're talking about ratios, right? We need 2-to-1. The ratio between these two gases, in order for a reaction to happen, we need 2-to-1. And this is that fancy word I talked about yesterday, that stoichiometry. It talks about these ratios. That's all that is. Okay. If I don't have enough H2, it's not going to happen. Okay. If I have way too much H2, then I need more O2 for it to happen, or else I end up with lots of leftover hydrogen gas. That is the simplest look at stoichiometry. We're not there yet. Okay. Number 10, it says click make ammonia. How many N2 molecules do I need to make products compared to how many H2 molecules? So again, it's going to ask me about the ratio. How many for each, right? So let's click make ammonia. And let's just throw a bunch in here, right? And let's see how much H2 I need. Whoa, okay. Let's balance it till I don't have any leftovers. Oh, look at that. Look at that. It's a 1-to-3 ratio, right? If I add, it's still a 1-to-3 ratio. 2-to-6 is the same as 1-to-3, right? Let me get my pen here. Just do a little bit of quick algebra, right? 2/6 equals 1/3, right? 2 compared to 6, I don't know if you guys know this ratio symbol, is equal to 1 compared to 3, right? So yeah, we can say 1-to-3. It's a 1-to-3 ratio. 1, oops. My stuff's like in my way. 1-to-3. Okay. All right. So I need, what is it? 1 N2 molecule. So 1 double nitrogen. when you guys went to type this, if you didn't use the subscript, if you didn't make the numbers here tiny, in Google Docs, it's just control and I'll show you. Format, text. It's just control, comma, right? That's fine. If you don't do that, it's fine. I know what you mean. If you said 1 and 2 like this, I would know what you meant, even though it's technically not what we were looking for. Okay, the next one asks us to click combust methane. And what do you think why do you think we sometimes have leftovers? So we're going to try and experiment to find out why we have leftovers. Okay. So let's say I have a bunch of methane. Okay. I have one molecule of oxygen and it's not going to react, right? I don't have enough oxygen in the container over here to cling on to these hydrogen atoms yet. But now I do. Now I do. We had a reaction. Okay. We had a reaction. But I still have some methane that is not reacted. I have some unreacted methane. I have a sense that I need more oxygen to make that happen. I still have some unreacted methane. So I need even more oxygen to make that happen. And I need even more oxygen. I don't have enough oxygen to react all of this methane. Okay. In this case, I have a reactant that limits my reaction, right? One of my reactants, I don't have enough oxygen to make this reaction happen. And so we're going to learn a new term. It is the limiting reactant. It is the limiting reactant. Okay. Sometimes we don't have enough of a reactant. A reactant for the reaction to this. I know that you guys couldn't have known that or written that into your work because we didn't learn that as vocab yet, but here we have it and we'll talk about it in the future. Without enough oxygen, fire won't happen, okay? If you have a propane grill and you somehow closed it inside of a container and you tried to light it, eventually the oxygen that was in the container would get used up, okay? And the reaction would happen and lots of heat and stuff, but you would run out of oxygen inside that container and then you would just be pumping just methane into the container, or I guess in that case propane, but it's the same chemically, it's close enough to the same thing. And so a candle, right? Methane is not too much different than candle wax. Okay, they're both hydrocarbons. If you're burning a candle on the kitchen table, and it's one of those big jar candles, and you pop the lid onto the candle, eventually the oxygen inside that container, the oxygen under that lid, it gets used up. It gets reacted, okay, and the flame goes out. The reaction stops because it runs out of oxygen. Because oxygen is the limiting reactant in that case. Now, if you run out of candle wax, you still have plenty of oxygen in the air, but now the candle wax becomes the limiting reactant because it's gone. It's all used up. All right. Here it asks us to draw a dot diagram of each of the products, and this translated wrong. I'm sorry about that. I did not take a close enough look at this when I converted it. Okay, so we're going to draw a dot diagram of each of the products. So it doesn't ask us to draw a dot diagram of the reactants. We're going to draw a dot diagram of the products in this reaction. I'm going to leave a little room here. I'm going to use my pen. I know, of course, on your version, you don't have like a touch screen and a pen to do this. So I'll forgive you if you skipped question 12. But for our review of this, I do want to show you. And I'm actually going to start with, my reactants because I think it'll make this clear. C. That's the right color. Okay, and then we've got our O2 here. Oxygen forms kind of a strange molecule compared to the covalent bonds we're used to. Oxygen will attach to each other. It's not as strong of a covalent bond as the ones we've talked about where they're all satisfied, and that's why oxygen likes to react with stuff. But this is good enough for now, right? We have 2 of these. And then we need our big yield sign here. We use purple for that. And this is going to give us CO2. Oops. Yeah. Sorry. And our water. And actually, there were 2 of those. Okay. So something we can look at here is, this carbon, it goes here. It becomes the center of that molecule, right? This hydrogen goes here. This one goes here. This one goes here. This one goes here. So the same carbons exist on the other side, right? The oxygens, we can see where they go. Right? And so we can see that in the reaction, none of these atoms disappear. None of this mass is lost. It's just that the methane, it gets broken apart and attacked by these oxygen molecules. And when it gets attacked, the oxygen attaches to the carbon. It replaces the hydrogen here with oxygens, right? And it attacks the carbon. It also attacks the oxygens. It attacks the hydrogens. And it forms new bonds. On the reactants side of the equation, on the products side of the equation, these molecules satisfy the octet rule. Okay. This takes less energy than this side of the equation. Okay. These oxygens are not happy bonded like this. And so they will tend to attack other things. They will tend to react with other atoms so that they can be happy, so that they can have these outer electron shells full. This is the driving force of chemistry. This is the arrow of time. This is what makes time happen in the direction that it happens. It seems to be, according to, really smart physicists. So that's our dot diagram of this reaction. Actually, just one of these reactions. These become these. And the same thing happened, right? the same thing happens. This carbon becomes this carbon, this hydrogen becomes this one, and so on. So I already sort of answered this question. Why do the oxygen atoms connect to the carbon atom? Why do these oxygens, why does this oxygen want to attach to this carbon? Okay. Why do the hydrogen atoms connect to the oxygen? Well, we answered that question up here with question number 4. Why do atoms come together to make compounds? They do this to become chemically stable. In other words, the oxygen atoms combine, they attach themselves magnetically, electromagnetically. The oxygen atoms connect themselves to the carbon atom, and the oxygen atoms connect themselves to the hydrogen atoms to become chemically stable, to satisfy their octet rule. So I'm just going to copy this answer. I'm going to bring it down here. And we'll put it in right here. This whole reaction happened because the oxygen wanted 8 electrons in its outer shell. This seeming desire of nature, okay, oxygen seems like it wants to do this, right? This is the octet rule. This tendency for atoms to hook up this way, this tendency to satisfy this octet rule, this is what causes chemistry to happen. This is what causes time itself to flow in one direction. Okay. I know that seems mind-blowing, but it's really a rather simple rule of chemistry and of physics. Okay. So hopefully that was an enlightening discussion of cheese sandwiches, right? And hopefully you guys messed around with this and you guys, what's the custom here? We got cheese and yeah. So hopefully you guys have seen that, you know, each sandwich, it might require a piece of meat to count as a sandwich, okay? We can see that in chemistry, we need different ratios of atoms in order for those octet rules to be satisfied, okay? Oxygen is going to need 2 electrons on its outer shell, and so its relationship is going to be 2 hydrogens to 1 oxygen, right? But if instead of hydrogen here, I had, if instead of hydrogen, I had beryllium, right? And beryllium has 1, 2 electrons on its outer shell, then it would be 1 beryllium to each oxygen, right? Right? So for beryllium and oxygen, it would be a 1 to 1, right? So it sort of depends on the octets. And now don't worry, we're not going to get, we're not going to be drawing a whole, excuse me, we're not going to be drawing a whole lot more dot diagrams, but it's enough to know that the rules for these ratios, these rules come directly from the octet rule that we've already learned. That's all we need to know, okay? All right. So hopefully that clears up how to make a cheese sandwich.